There is a bridge that has been under continuous construction for over 500 years, and it has never once required a repair crew, a concrete truck, or a single bag of cement. This is a living root bridge, and unlike every other piece of infrastructure ever built by humans, it does not degrade with age. It gets stronger. Some documented bridges in northeast India have carried foot traffic daily for over 2 centuries and are rated to hold the weight of 50 people simultaneously, using a structure that has never stopped growing since the day it was started. Yet I'd bet you've never crossed one, nor are you likely to anytime soon. So what is a living root bridge? How does it actually work? And why, in an age of steel and concrete, are people still choosing to grow their infrastructure instead of building it? To understand the brilliance of this system, we have to go back over 500 years into the hills of what is now Meghalaya, a state in remote northeast India defined by some of the highest rainfall totals on Earth. The Khasi and Jaintia tribes who settled this region faced a problem that no amount of carpentry could solve. During monsoon season, this area receives over 450 inches of rain annually, turning narrow valley streams into raging torrents capable of destroying any wooden bridge within a single season. A structure built from cut timber would rot in the humidity within a few short years, and a bridge that failed during monsoon season didn't just mean inconvenience. It meant villages cut off from medical care, trade, and each other for months at a time. So generations of Khasi builders, whose individual names history never recorded, arrived at a solution that no engineer trained in Western construction methods would have considered. Instead of fighting the jungle's growth, they decided to direct it. They identified the Ficus elastica, the Indian rubber tree, a species whose secondary roots grow not downward into soil but outward along any surface they touch, seeking moisture and structure wherever they can find it. Builders would plant these fig trees on opposite banks of a river, and as the young aerial roots began to emerge, they would guide them across the water using a temporary scaffold. Traditionally, the hollowed-out trunks of areca nut palms split lengthwise into root-guiding tubes. This same underlying logic, training a living organism into a permanent architectural form, echoes what later became known in the West as arbor sculpture, but nowhere was the principle applied at structural, load-bearing scale until the Khasi people did it centuries earlier, out of necessity rather than art. The core engineering problem a living root bridge solves is one that every conventional bridge on Earth eventually loses to: entropy. A steel bridge fights corrosion from the day it's installed. A concrete bridge fights water infiltration and freeze-thaw cracking from the moment it cures. Every material humans have ever built with begins deteriorating the instant construction finishes. A living root bridge does the opposite. Because the structure is composed of living tissue, it continues laying down new growth rings and thickening its load-bearing roots for as long as the tree itself survives, meaning the bridge's structural capacity increases with every passing decade rather than decreasing. The mechanism relies on 3 biological principles working together. The first is root plasticity. Ficus elastica roots are unusually responsive to physical guidance, and when trained along a fixed path using bamboo or palm trunk scaffolding, the root tissue will grow to conform to that shape permanently, fusing to the guide structure over a period of 10 to 15 years until the scaffold itself is no longer needed and can rot away, leaving pure living root behind. The second principle is self-grafting, known botanically as inosculation. When 2 roots from the same tree, or from trees on opposite banks, come into sustained contact under tension, their vascular tissues fuse together into a single continuous structure. Exactly the way a graft heals on a fruit tree. Over years, dozens of individual root strands inosculate into a dense, load-distributing lattice, functioning less like a single beam and more like a woven cable system. where the failure of any one strand simply redistributes load to the hundreds of others fused around it. The third principle is continuous secondary growth. Unlike a steel cable, which has a fixed cross-sectional strength the day it's manufactured, a living root thickens every growing season for the entire life of the tree, which for Ficus elastica can exceed several hundred years. A newly matured bridge might support a handful of people cautiously. A bridge 2 centuries into its growth cycle, with root trunks as thick as a human torso, can support entire wedding processions. And this biology produces properties that no engineered material can replicate. The first is self-repair. If a root section is damaged by flooding or falling debris, the surrounding living tissue will grow to compensate and reinforce the wound, something no steel truss has ever done on its own. The second is flood resilience, a direct consequence of flexibility. A rigid bridge meets floodwater with resistance and eventually fails. A living root structure flexes and sheds debris, and its root system continues stabilizing the riverbank itself, actively preventing the erosion that destroys the foundations of conventional bridges nearby. Botanical and engineering researchers have begun quantifying what Khasi builders understood only through generations of observation. Field studies conducted by researchers including Ferdinand Ludwig at the Technical University of Munich, who has spent over a decade documenting these structures, have measured individual bridges spanning over 50 meters with root diameters thick enough to be structurally analyzed using the same load calculations applied to timber trusses, confirming tensile and compressive properties that rival engineered wood products, all generated by a tree that was never cut down. So if a living root bridge requires no maintenance crew, no replacement schedule, and actively improves with age, why isn't this the standard for infrastructure in flood-prone, rural regions worldwide? The answer starts with time and the same economic logic that has sidelined nearly every passive system this channel has ever covered. A living root bridge takes between 15 and 30 years to become fully load-bearing. No government infrastructure budget, no development bank loan, and no modern construction contract is structured around a 3-decade build timeline. Concrete infrastructure is fundable specifically because it is fast, quantifiable, and deliverable within a single fiscal cycle, while a growing bridge cannot be finished on any predictable schedule and generates 0 billable hours for a construction company once the initial planting is complete. There's also a knowledge transmission barrier. Guiding root growth correctly requires intimate generational familiarity with Ficus elastica behavior, something that exists almost exclusively within Khasi and Jaintia oral tradition. As younger generations migrate to cities for wage labor, the specific skill of root guiding is fading, and UNESCO has flagged several of these bridge-building lineages as at risk of disappearing entirely within a generation. And then there's a scale and geography problem. Ficus elastica only produces this behavior reliably in consistently humid, high rainfall tropical climates. This isn't a technique that transplants to Kansas or Kazakhstan. It is a hyper-regional solution precisely calibrated to one of the wettest ecosystems on the planet. So the real question becomes whether any part of this principle applies beyond Meghalaya. And increasingly, the answer is yes. Ludwig's research group has begun applying inosculation and guided growth principles to living architecture projects in Germany, using different tree species suited to temperate climates to grow pedestrian bridges, walkways, and building facades that similarly strengthen with age rather than degrade, with early prototype structures already load-tested for pedestrian use in controlled trial sites. For anyone drawn to this idea on a smaller scale, arbor sculpture techniques using species like willow or sycamore can be applied to garden structures, living fences, and small footbridges over ornamental ponds, using the same root and branch grafting principles at a scale a determined landowner can manage without decades of specialized tribal knowledge, though full structural load-bearing results still require a minimum of 10 to 15 years of guided growth. Maintenance, in the years before a bridge becomes fully self-supporting, is simple but essential. The scaffold guiding young roots must be checked seasonally to ensure roots are growing along the intended path rather than drifting, and periodic pruning of competing growth prevents the tree from directing energy away from the bridge structure itself. A living root bridge takes a single insight that a structure doesn't have to be built once and then decay. It can instead be started once and grown forever, and turns it into infrastructure that will very likely outlive every person who ever walks across it. A lot of what this channel covers works exactly as claimed, costs less than what replaced it, and was set aside not because it failed, but because it doesn't fit inside a fiscal year. If that's the kind of thing that matters to you, subscribing and sharing is the simplest way to make sure it keeps being found. And if you want to see how a 500-year-old Incantera system created its own microclimate precise enough that NASA is now studying it to grow food on Mars, then that video is up next.